So dear audience, today I am going to discuss about DC load line and stability of a transistor. So now to discuss about DC load line, first we have to draw the circuit diagram. So we'll take first common emitter configuration. We know everyone. This is RV. This is input side. Output side. We are taking NPN transistor. This is C out. This is C in. This is RV. This current is IV. This is RC. This current is IC. The power supply, this is plus VCC. Okay. Now this voltage is base to emitter voltage VBE. This voltage is VCE, collector to emitter. Now we will use KVL. Where? We will use KVL in the output side, output terminal. So in this path, VCC, ICRC plus VCE. So using KVL in this path, we can write VCC is equal to simply VCC is equal to total source voltage, that could be IC into RC plus this collector to emitter voltage, that is VCE. Say this is number one expression. Now we'll draw the output characteristics of common emitter configuration. So this is in this direction, it should be VCE. Along y-axis it should be IC with different IB. Suppose this is IB is equal to 0 microampere. As we know, base current is very less, it is in the order of microampere. So these are different base currents. So this is IB0 is 0, it may be IB1 in general, I am telling. IB2, this is IB3. So this is IB is equal to 0, this is less than 0. So this part is cutoff region, and we are considering this region is saturation. So saturation, this portion is cutoff region. Now what we get is that this is the expression. This is very, very important expression. Now along x-axis in this graph, along x-axis means along VCE axis. So along VCE axis, what is that? IC is equal to collector current is equal to 0. As you know, along x-axis y is equal to 0, along y-axis x is equal to 0. Now if we put here IC is equal to 0 here, so VCC is equal to ICRC plus VCE. Now IC is equal to 0, so VCC is equal to VCE. So that means the collector to emitter voltage is maximum, this is VCE. So this is one important. So suppose along y-axis, now along IC axis, what will happen? VCE should be 0. So in this expression, if we put VC is equal to 0, so VCC is equal to IC into RC. That will give you IC is equal to VCC by RC. So say for example, take the red line, this one. Suppose this point indicating VCC, VC is equal to VCC. This point is VCC. And this is one more expression, this is the most important expression. IC is equal to VCC by RC. So this point is VCC by RC. So now if this point and this point, if you join, this straight line will come. So this line is called DC load line. DC load line. Now this DC load line intercepts the base currents here, here and here. So the intersection of this DC load line and the IB curve creates a operating points or quiescent points. So now, say for example, we are considering this is a operating point, Q point at the mid of the active region. We know that this is cutoff region, this saturation, and this portion is active region. This one is active region, This portion is active region. Now, what will happen? This is Q point. Now, to fix a Q point, what we will do? This Q point. So, how to fix a Q point? If this is the Q point, so that means this base current IB2, this corresponding voltage VCE, that should be VCEQ. This IB2, it should be IB2 is equal to IBQ, and this corresponding collector current, this is ICQ. So IBQ, ICQ, VCQ, that representing the operating point. So now I can erase this part. So now in the next part, what we'll do? So DC operating point or quiescent point Q could be represented by VCEQ, ICQ and IBQ. These are fixed. Now Q point is fixed in this position. Now for a particular type of amplification, this Q point should be constant. It should not be changed. So when we use some base current, suppose this is base current, then what will happen? When this base current increases, then Q point will shift to this position. When this goes to 0, then it will again come back to this position. Again it goes negative, it will come to this position. When it goes to from negative to this 0, it will again come back to this position. So when the input signal rotates first 180 degree and second 180 degree, it will go up to this point, again come back, again goes to negative, again it will come back. So total 360 degree, one round. Then what should be the waveform for output voltage and current component? We'll discuss it. So now this is current change. So when this Q point goes to this one, so current will change in this way. What should be the VCE changes? How VCE will change? That I will show you. This. So when this Q point moves to this, for positive half, it will be like this. So when this to this, voltage will be like this. When this to this, voltage will be like this. Now from this curve, these three, this and this, it is very clear that when the input goes to positive side, it goes to reducing. That means the input and output, there is a 180 degree phase shift. As we know that common emitter configuration gives 180 degree phase shift in between input signal and output signal. So that is clear here. So we are getting the full cycle at the output, the collector current and the VCE swings. But now if this Q point shift to near to the saturation point, or this Q point shift to the near to the cutoff region, then what will happen? Why Q point should be fixed? For a particular type of amplifier, Q point must be fixed, or it should be midpoint of the active region. So Q point, the general formula is that Q point must be selected at the mid of active region, so that we can have full cycle at the output. But what will happen if we select Q point nearer to the cutoff or nearer to the saturation point? That I want to show you. Now let us draw the waveform again. This is VCE axis, this is IC axis, and different current. Suppose DC load line is this. So this is IB0, maybe IB0 microampere. So this is nearer to the saturation. So IB, and this is middle. Suppose IB1, this is IB2. Now instead of Q point here, if we select Q point in this position here, then what will happen? If suppose Q point is this position we selected, then what will happen? Again, if we use base current here, now when this positive half comes, this Q point shift to the active region, maybe this position, very close to 0, because VC now is very close to 0. Again, when it goes to negative side, it will come to maybe this position. Then what will happen? Okay, or this position, maybe like this symmetric nature. So one more IB is there. So suppose Q point shift to this position, then what will happen? So this is line and this line. This is very close to 0. So when it goes to saturation, then we don't have any output here. But when it goes to negative side, we will get some voltage this type. So only positive half we are getting some voltage, but here we don't have only for this negative half. For this half we are getting at the output. So that is VCE swings. This is VCE maximum. For the positive half, we are not getting any output voltage. So that means if we select Q point nearer to the saturation region, then what will happen? Then the positive half of the input will be clipped off at the output of the amplifier. So this is the main problem. Now if we select Q point nearer to the cutoff region, then what will happen? Again we will draw the waveforms. This is VCE axis, this is IC axis. Now this is IB is equal to 0 microampere. This is one more current, this is one more current. Now this is DC load line. Now Q point is selected nearer to the cutoff region. This is Q point. Then what will happen? Now this is the midpoint. So when take the base current variations, suppose base current is changing like this. So for positive half, no problem, it will go up to this, suppose. So in that case we are getting VCE, and correspondingly IC also will be there. Okay, IC current will be there. Here also we can draw the collector current also. For collector current, for negative half will be 0, for positive is nothing, so negative half will be 0. So similarly here also, for when it moves up, then we'll have the collector current, and similarly the VC. But when it goes to the cutoff region, then there is no current flow. So that means that time the output will be 0. So when the Q point, that means what is that? A Q point is selected nearer sorry selected at the cutoff region or nearer to the cutoff region, then negative half of the input will be clipped off from the output of the amplifier. So the conclusion is that if Q point selected nearer to cutoff, then negative half will be clipped off at the output. If it is selected nearer to the saturation, the positive half will be clipped off. But if it is selected at the midpoint, then both half will be available. So these are three conclusions are most important. So finally we can say that Q point must be selected at the midpoint of the active region whenever we are going for using a transistor as amplifier. So Q point should be selected at the midpoint of the active region. So Q point must not be changing throughout the operation. But due to some inherent property of the transistor, Q point changes. How Q point changes? Q point changing by 3 parameters. So mainly the temperature change. Due to temperature change, Q point will change. How? Due to temperature change. Temperature change. We know that every 10 degree rise of temperature, ICO, the reverse saturation current, is doubled. Doubled. It will be doubled. Suppose ICO is 2 microampere at 20 degrees centigrade, say for example. Now it increased to 30, that means 10 degree rise, it will be 4 microampere. So it will be doubled. Now we know that if ICO changes, then what will happen? If ICO changes, then what will happen? We know that IC is equal to, collector current is equal to beta IB, beta plus 1 into ICO. So beta plus 1 into ICO. Now if ICO increased somehow due to temperature increment, if temperature increases, then what will happen? Minority carrier will be increased due to avalanche breakdown. So minority carrier will be increased. One minority carrier increase means covalent bond breaks, minority carrier increase, so ICO will increase. So ICO increase means beta plus 1 is a large quantity. If beta, suppose beta is 99, then beta plus 1 near about 100. So 100 into ICO. If ICO is small change, that is multiplied a large quantity, 100. So that means beta plus 1 into ICO will be large quantity. That is beta plus 1 into ICO, that should be large enough. It will increase. And that will added with beta IBO. So ultimately what happens? ICO will increases highly, enormously. So IC will increase. So when IC increases, then what will happen? We know that heat is equal to current square R into T. So this current increase means a collector current increases. So that means collector current increases means heat will be increased. Heat increasing means the device temperature will increase. Then what will happen? Due to increment of IC, what will happen? The device temperature device operating temperature will increase. Once the device temperature increases, then what will happen? Minority carrier again breaks. Minority carriers will be increased due to the breaking of covalent bonds. One minority carrier increase, that will enhance the ICO. Once ICO increase, beta plus 1 into ICO will be increased again ICO will be increased. Once IC increased, I square RT, that will be more, heat will be more. So in this way, it will be increasing ICO and heat. Ultimately, at a stage will come, the device temperature will be enormously increasing and the transistor will burn. If transistor is burned out, then this is called thermal runaway. What is called? Thermal run away. So this is not desirable because transistor will burn. If transistor is burned, if we replace the same transistor, same type of transistor, but still the beta value will change. Beta will change. If beta change means the other current components also will change. So once the other current component will change, IB will also change, so IC will also change. So when IC will change means Q point again will be changing. So due to temperature variation, beta changes, ICO changes. Similarly, VBE also there, base emitter voltage. We know that due to temperature variation, minus 2.5 millivolt per degree centigrade. So each degree centigrade temperature rise, VBE reduces minus 2.5 millivolt. So that means that will hamper, that will also reduce, that will also change the current component IC and ICO. So that will also hamper Q point. So Q point may change due to three parameters. Number one is ICO, the reverse saturation current. Second one is VBE, and third one is beta. So these three parameters all are temperature dependent. Any one changing, the Q point will change, and the operating point will change, means the characteristics or the performance of the device will change. Our target is to make Q point fixed at its original position where it was selected initially. That is the midpoint of the active region. So we have some parameters to study the stability, because Q point must not be changing. So that means Q point must be stable. So how much the device is stable, that we will be calculating with some parameters. That is called stability factor. The name is stability factor. Stability factors. So these stability factors are also three kinds: S prime, S double prime, for due to these three parameters: ICO, VBE, and beta. For these, so what is S? S is del IC by del ICO, keeping beta and VBE constant. So rate of change of collector current with the reverse saturation current, that is called the stability factor S, keeping beta and VBE constant. Similarly, S prime, one more parameter is there, S prime, that is the rate of change of collector current, that is del IC by del VBE, the base emitter voltage, keeping beta and ICO constant. So that is S prime. So S double prime also is there, del IC by, now remaining is beta, so del beta, keeping VBE and ICO constant. So these parameters are there. So these are called S prime, S double prime. And what is S? Already I mentioned, del IC by del ICO, keeping beta and VBE constant. So we will calculate the stability factor for different circuit connections. So now we understood what is stability factor, how many stability factors are there, how they are related, how they are changing the stability of the transistor, what is thermal runaway, how thermal runaway is initiated, all these things we studied. Now we'll calculate stability factor. Stability factor is primarily for three different circuit configuration. First one is fixed bias circuit. Fixed bias circuit. Second one is collector to base bias circuit. Number 3 is potential divider circuit. Self bias or emitter bias or voltage divider or potential divider circuit. For these three, so first we will consider fixed bias circuit. So we'll first draw the circuit, the fixed bias circuit. So let us first draw the fixed bias circuit. Now here we'll use NPN transistor. So first draw the circuit. This is the collector resistors. The current flowing is IC. The base resistor is connected to this region. This is output capacitor. This is input side capacitor. So C in we can write, C out we can write plus minus. So this is NPN transistor. So the power supply is plus VCC. Okay. So now this is RB. The current is IB. This is VBE potential base to emitter. This is plus, this is minus, this is VCE potential. Now we will consider this path, the input side. We will use KVL at input terminal, input side. Then what will happen? So VCC is equal to this path, this direction. I can show you by black line, black to VCC, this direction, this up to this. So this path we will take KVL, Kirchhoff's voltage law. So according to that, the VCC should be VCC is equal to IBRB plus VBE. But we know that VB is very small. So later we can neglect it because VBE is very less with respect to VCC. So here what is IBRB is equal to VCC minus VBE. So what is IB? So VCC minus VBE by RB. Now we know that VCC is very greater than VBE. So we may neglect VBE. Generally it is 0.7. So we may say that it is VCC by RB. So that is your IB. So we may say this is number 1 expression. Now we know that IC is equal to, already I wrote beta IB, beta plus 1 into ICO. This is the expression. This is a very famous expression. Now we got the IB. So what is IB? Beta into we got the IB. IB is equal to VCC by RB. So VCC by RB plus beta plus 1 into ICO. So this is the expression. This is IC. So this is IC. This is very important expression. Now what is S? S is equal to del IC by del ICO, keeping beta and VBE constant. This is most important. So now we differentiate this expression with respect to ICO. Then what will happen? So these all are constant. Beta constant, VCC constant, RB constant. So del IC S is equal to del IC by del ICO. What will happen? It will be beta plus 1. So it will be beta plus 1. So it will be beta plus 1. So S is beta plus 1. So if beta is equal to 90, 49, suppose beta is 49, then beta plus 1 should be 50. So that means IC, that means IC increases 50 times faster with respect to ICO. 50 times faster. So it's very high. So the value of is higher, representing the lower stability. So this stability factor should be as low as possible. Then the stability of the system or the device will be more. So here this system is less stable only because it almost 50 times faster with respect to ICO. IC changes. So this is not at all good circuit. This is fixed bias circuit or the base circuit. Now we will go for collector to base bias circuit, the second one, collector to base bias. So fixed bias circuit is finished. Now we will go collector to base bias circuit. So let us draw the circuit first. Collector to base bias circuit. So collector to base bias circuit, first we draw the circuit, this one. This is the collector part, this is plus VCC, this is RL or RC, whatever, the load resistance we can say that RL. This NPN transistor. Now collector to base. So this is collector to base. This is the circuit. So that's why it's called collector to base. Collector to base. So that is RB. And this current is always IB. This is VBE. This is now this current IC. So this current should be IC plus IB. Why? Because this is IB current, this is IC current. So this current should be IC plus IB. And this voltage is VCE. This is plus, this is minus, this is plus, this is minus. So this is NPN transistor. So here also we can like this draw some capacitor here like earlier circuit. This is not important. C in, C out. Correct. So this one. Now we will use Kirchhoff's voltage law, KVL, where VCE is equal to this portion, VCE, this portion. I can show you the path, this path. So here that is VCE. So VCE is equal to, we can write IBRB, this IBRB plus VBE, this one. Now this path, now this direction, we can get one more KVL. We can write this number 1. So in this direction VCC is equal to RC into IC plus IB, or this is not RC, we are writing this is RL plus this VCE, this voltage VCE. So this is the expression number 2. Now this VCE, this is VCE, we get VCE, so we can put this value. So ultimately VCC is equal to IC plus IB into RL plus IB RB plus VBE. This we put here. Now we know that from here we can find out IB, because we have to find out IB. So now IC RL plus IB RL plus IB RB plus VBE is there. Now take IB common. So RL plus RB plus IC into RL plus VBE. So now we can say that VCC minus VBE minus IC RL, that is equal to IB into RL plus RB. So here IB is equal to this by this. So IB is equal to, we can write VCC minus VBE minus IC into RL divided by RB plus RL. So this is most expression, important expressions. If we give 1, 2, 1, 2, this is must be 3. Now we know that, everybody know that this expression, the important one, IC is equal to beta into IB, beta plus 1 into ICO. So we know IB, so we will put the value of IB here. Okay, so IC is equal to beta into this big expressions, that is VCC minus VBE minus ICRL divided by RB plus RL, this IB, then here beta plus 1 into ICO. This is the expression. Now IC is here, here also IC is there, so IC we have to take common. So here IC, now if we take in this direction, beta into this minus will be plus IC into beta into RL, beta into RL divided by RB plus RL. So this is left side, right side, beta VCC as it is minus VBE as it is divided by RB plus RL as it is, then beta plus 1 into ICO as it is. Now we take IC as common. So IC if we take common, so it will be 1 plus beta RL by RB plus RL. So that is equal to beta as it is, we can write it beta VCC minus VBE divided by RB plus RL plus beta plus 1 into ICO. This is the expression. Now we can differentiate it with respect to ICO. Now here all the parameters are constant. So if we differentiate this, S is equal to del IC by del ICO, keeping beta and VBE constant, then what will happen? This full should be 0, this full part, because all are constant, so this should be 0. And here del IC by del ICO, it should be this into del IC by del ICO. So it should, and beta plus 1. So beta plus 1 at the right side and divided by this factor will come here. 1 plus beta RL by RB plus RL. So this is the final solution. So beta plus 1 by this one, big ratio. So ultimately what we get? We got it S is equal to beta plus 1 divided by a factor that is 1 plus beta RL divided by RL plus RB. That is only we get RB. So now here in the fixed bias circuit, S was beta plus 1 for fixed bias circuit, but collector to base bias beta plus 1 divided by a factor, big factor. So that means in this collector to base bias circuit, the stability factor is lesser than the collector to a fixed bias circuit. Collector to base bias circuit, the stability factor for the collector to base bias circuit is less value than the fixed bias circuit. So that means the stability of this collector to base bias circuit improved. So the stability of the collector to base bias circuit is improved with respect to the fixed bias circuit. This is very important. So this is enough for the today's class. So this is enough for the today's class. In the next class we will go for cell bias circuit or the voltage divider circuit in the next class. So till then stay tuned, we'll meet again. Thank you.